So now we have kind of unspeakable related to unthinkable. This is unspeakable because we don't really know how to compute these eigenfunctions and eigenvalues. It's rather difficult. So we know how to solve these problems in one dimension and two on a computer. We can sometimes do a reasonably good job in one dimension looking at some unimodal map. And the reason why we can't do this is that even if you try to do, so maybe I'll put it in chaos book, right now it's not there. If you try to find the most important of all eigenfunctions is the 0 one, which is called natural measure. So phi 0 of x is called natural measure. So this is what you obtain by noisy computer iterations, I mean imperfect computer iteration. If you just look at long-time dynamics, you find that in some regions you're more likely to be, in some regions less, and most of the space not at all. Because usually these attracting sets where dynamics settles in at long time are smaller than the embedding space itself. And even when you do it for some totally simple, so of course in Chaos book I have one example where you can analytically compute this measure and it equals 1. But that's the only one example. That's called ULA map, and you can, well no, it's actually not 1, but it's, 10th map has one ULA map. But if you just take any bimodal map, unimodal map, just with two branches, which is not parabola, and you start numerically computing this row, 0, the natural measure. So this is defined on interval to 0, 1. So what you can do, you can just start someplace, and you can iterate. You start someplace, you iterate, go someplace else. And as you do this, you're filling points on unit interval, and you can box them. You can do this. It's very cheap to do this for a million times or whatever. And you'll get something totally horrible. You'll find that it's singular every place. And if you blow it up, it'll be singular. It has very good reasons to be singular, so it's not surprising. So this thing that mathematicians feel totally comfortable with because they say, oh, the measure is continuous on unstable attractor, we prove it, there is axiom, blah, blah, blah. That's because they don't have to work. If you actually do this thing, it's just horrifying. So what happened to that thing in the trace formula? How did we, the whole point of all Chaos book is that you don't do this. Because you can't do this, and it doesn't make sense, and just crazy things to do. So how did the trace formula circumvent this? What the trace formula says is that dynamics has some simple law. So as you'll see, these contributions will be organized by shortest period to longer and longer. I'll explain why, but basically this volume is shrinking exponentially. So longer periodic orbit exponentially small compared to the short ones. And in short time, we have very simple dynamics. In short time, if you start with a smooth function, you get another smooth function. This you get only at infinite time. This, incredibly crazy thing. So what periodic orbit theory says, look, the way I've constructed this, at long time it looks complicated, but I've done this by doing the same thing over and over. Totally boring, repetitive motion. I do this, I apply this map, I apply this map, I apply this map. It's totally innocent in any single iteration. And by using this finite periodic orbits, I have a good description of neighborhoods here. And then it turns out that longer solutions, and that's the point of today's lecture. I'll show you don't actually use trace map, you use the determinant, not the trace formula to compute things, have a property that these short repetitive motions are dominant. That's what we did when we look at these finite dimensional transition matrices. We define fundamental part of the cycle expansion, things that describe qualitatively the most important thing that happen in dynamics. And the rest turn out to be super exponentially small corrections. So by understanding topology, this unspeakable formula, which has infinitely many prime orbits, each one of them repeated infinitely many times. So there's no way in the world you can compute this. Same thing on the left-hand side. No way in the world you'll compute infinitely many eigenfunctions of this. We can only do it for harmonic oscillator analytically, and that's the end in quantum mechanics. So there is, and here there's some examples where I can do it, but they're similarly silly. So So that's the meaning of trace formula.